Yeah, I'm ready to go. Hello, everyone. My name is Kyle Almekinder. And I am a Master's of Science student with the University of Arizona. And today I'd like to discuss my capstone project using spectral indices to determine the effects of the 2021 summer North American heat wave at Mount Rainier, Washington. Okay. A little introduction about this project. The North American heat wave hit last year between late June and early July for about 10 days. And this is not uncommon for heat waves in Washington or in the Pacific Northwest, but this particular one was considered a 1,000-year heat dome. And it just kind of settled over the region for that time span. And it forced normal weather patterns to go elsewhere. And it just really allowed this heat to sink in and just raise the normal average temperatures over 20 or 30 degrees above average. And the map you can see on the right was on June the 28th, and over 250 records were broken across the Pacific Northwest, including Seattle. As you can see, it's 107 degrees on that map. It eventually reached 108 degrees, which set a new record for Seattle. And they'd only seen triple digits twice before this. And the state of Washington itself set a new record of 119 degrees on the eastern side of the state. And today's project is going to be revolving around Paradise, which is right here near Mount Rainier. And their average temperatures I will get to, but it was over 90 degrees at one point. So the project goals today were to analyze the effects that the heat wave had at the mountain from 2015 to 2021. And I focused on the end of the summer because I wanted to see what the full extent of summer temperatures were for the whole mountain, and not just this heat wave, because I figured since it started in June, it probably was going to endure some more heat over the next few months, June, July, August, and even September. And I wanted to see a few different things. For the analyses, I wanted to see the current snow presence on the mountain, using the NDSI, which is normalized difference snow index, the vegetation health of the mountain and its surrounding park boundary, using the NDVI, which is the normalized difference vegetation index. And I also wanted to see how the glaciers reacted to this by just measuring general area versus a benchmark several years ago. Study area is Mount Rainier and Mount Rainier National Park, highlighted in the pink on the map to your left. It's the highest point in the Pacific Northwest at 14,410 feet. It's about an hour from the Seattle-Tacoma metro area. 97% of the park is designated as wilderness land, and mentioned previously, the Paradise temperatures range in the 50s and the 60s in the summertime, as highs, and 40s in the lows. So using this as kind of our control point, we're talking 30 degrees above average. The data for this project was used from Landsat 8 imagery that I collected from the USGS GLOVIS interactive website. And I wanted to have at least, at most 50% cloud cover on each image. I ended up having to do a 5-year study period. I wanted to keep it short enough that I could see some different changes, but not long enough to be overwhelmed with the data. And then just supplemental GIS data was collected from ArcGIS Online and other local government outlets. The main methods for this project were to correct the images that I had collected. Without this, it wasn't going to, the data was going to be very biased. So to do so, I refer to the Landsat 8 User's Handbook. And in that requires some calculations using different numbers that were collected in the satellite. Reflectance and sun angle are two of the ways to correct these images for atmospheric bias. Sun angle, as mentioned, is how the satellite is angled as it passes through the Earth, so around the Earth. So these calculations help correct it so that we have a perfect image before we can proceed for further methods. To calculate the two spectral indices, NDSI and NDVI, both are very similar in their processes. They have a combination of bands of subtraction and addition. Both produce a range from -1 to 1. And from some research, I wanted to reclassify both. The NDSI did a range from -1 to 0.4 and 0.4 to 1 that would separate out snow from glaciers and ice. NDVI, I reclassified from -1 to 0 to show dead or inanimate objects. 0 to 0.33 would be unhealthy vegetation. 0.34 to 0.66 is moderately healthy, and the remaining 0.67 to 1 is the healthy. For both, I also created a mean average NDSI for all the whole years. And then I also wanted to create a year mean difference just for more data to see if there were any more anomalies or things that I could measure. As for the glaciers, I reclassified the NDSI results and compared them to a 2005 glaciers data set that I pulled from Pierce County, Washington. For the results, the normalized difference snow index showed a significant decline over the study period. From 2015, it started at 14.29%, and it made its way down to 8.60% last year, with an average of 10.25. So there was a small uptick in 2020, but for the most part, it was a pretty significant decline. I also tried to create a year mean difference maps, but these were much more inconsistent and really didn't tell the full tale of what I was seeing from this method. And here are two maps of the NDSI. On the left is its raw output, and the range 1 to -1, it shows the one where the blue shows the difference of snow present, or it shows snow presence, and then the red would be the lack of snow. And then on the right is the classified version of just snow on the presence, and you can kind of see part of other parts of the park. As for the vegetation, I saw that it was a much stronger correlation with the yearly temperatures. The above graph on the upper right-hand side shows the percentages of the healthy versus unhealthy vegetation over the course of the 5 years. And then below is the reference of the summer temperatures. 2021 had the lowest percentage of healthy vegetation. And I mentioned that because in 2018, it shows a 60.4% healthy rate, but that's actually an anomaly, and I'll get to that in a second. So if I take that out of the study period, again, last year showed its lowest point. As mentioned, on the left is the 2018 map, and we see a lot of red, but that's because the image, the raw image, was actually covered in clouds, and the NDVI calculations interpreted that as dead vegetation. So taking that out of the equation, I saw that 2021 produced the lowest percentage of healthy vegetation. But it is interesting to see that it interpreted it that way. So just another thing that I needed to take a second look at. And then on the right-hand side is a 2021 image for comparison. And you can see a lot of healthy and moderately healthy, but there is still quite a bit of dead and inanimate vegetation, which would be the rocks and ice and snow on the mountain. As for the glaciers, similar to the vegetation where it saw a strong correlation with the summer temperatures, again, 2021 had its smallest glacial size. This is just a comparison from the 2005 data set. So 2021, 63% of the yearly glacier size of the 2005 data set. So, and then each year as the temperature got cooler, the glacier size increased and vice versa. So it was interesting to see how that changed over the 5 years. Conclusions. On the right-hand side is an animated image of all the different colors of the maps for the natural color images of each year. And it's pretty clear that the snow is receding in each image, and the last one is 2021. The snow index was more conclusive on a macro level, I thought, in specific locations of the park and of the mountain. Glaciers had a downward trend, and I saw that the vegetation worked the best. It gave the best result to see how this heat wave affected the whole area. I had some limitations. The NDSI is useful for simple analysis. I thought that it was great to see a specific result, but there's a little bit of confusion, especially with it being a binary reclassification. It really grouped things into one or the other. So it didn't give me the best results. It assumes a digital terrain model surface, meaning there's nothing else on the ground. But we know that that's not the case. There are rocks and crevasses and trees and canopy cover. So when I did this research and this project, we know that there's possibilities of snow underneath the canopy. So it's possible that there's a lot more snow on the ground than what the results showed. As mentioned, the vegetation index cloud cover, it produced a pretty significant biased result in the 2018 image. So that skewed my results a little bit, but it was still good to see that it was able to calculate correctly, and I just had to omit that from some of these talking points. And then the glaciers are also generalized. 2005 glacier data set, as it was stated from when I downloaded from Pierce County, Washington, isn't a true data set for the actual area of all the glaciers. It was more for a map use only visualization. So I just had to work with what I had. And then I also came up with a few future cases for this project. I thought that I could repeat this frequently every year. We're going to have summer temperatures and at Mount Rainier. So if we were to add each year to the end of this project, we can get a much larger understanding of the temperature changes over time. Being at the site for sure would be a great useful tool to help combat the digital terrain assumption. I could measure how much snow might be underneath the canopy cover, if possible. Also get other measurements that are in maybe shadows or other places. Ecosystem health, such as rivers and salmon, and then also pulling other imagery. I only used Landsat 8, but now we have Landsat 9 imagery that was just launched last year. And there's also a few other satellites such as Sentinel-2 and LIST-3 that can be used. So getting all sorts of different imagery can help with the analysis moving forward. Thank you.